किनकि हाम्रो सबैजना अगाडिकै सर म्यामहरू आउनु भएको छ। सो अरू पनि जोइन गर्दै गर्नु होला। आज हामी डे 6 के अरे हाम्रो सेमिनार 6 मा छौँ। सो टेक्निकली यो सेसन हाम्रो 7 हो हाम्रो
We
फर्स्ट
started
सेसन
with S0.
हवस्।
We are mathematicians, we started with S0. So our
हुन्छ
number system starts with 0, not 1. Okay, thank you. So this is the mathematics throughout this ages series, the fame history of mathematics. Today's title, it has been already announced, is Abracadabra, and I have added some interesting family known as Bernoulli family, because I have to have a 1.5 hours presentation, so my slides should be over 100 in my opinion. So I'll be joining two parts in almost all, not in all. So this is Abracadabra and Bernoulli family. I hope that most of you or all of you know what is this word abracadabra. So before I tell the meaning of this, which you know again, I'll try to show one slide over here. This one, abracadabra. So you see, this was a talk. I'm borrowing a talk, my own talk, which I have gave to the Department of Tribhuvan University on April 26, 2004. So it's a 17 years old presentation. But I think that it is a very interesting talk on mathematics and on talking about very simple mathematics and try to relate simple mathematics with bigger mathematics, I'll say like that. So you see, when I gave this talk at Central Department of Mathematics at Tribhuvan University on April 26, 2004, this was Central Department of Mathematics at the time. Not actually photo from 2004. This is some 1+ years photo only, because Raman sir is here. He is already in the wheelchair. So it was our small program was going on. We had a good photo over here just to show that this is Central Department of Mathematics, a historical department of mathematics in Nepal. So when I gave the talk, so when I put this title, Abracadabra, then I told the audience, our students of master's level, they were students from our central department. Also, they were students from Central Department of Math Education. I asked him, what is this abracadabra? Nobody could give the answer. Only lastly, Gajendra Thapa, Sir Gajendra Thapa, only he was able to give the answer. He was saying that, yo bhaneko cha ta jantra mantra ho. He was saying like that. Anyway, so abracadabra is jantra mantra, putting a sheep and converting into a line, something like this. Anyway, so that's why I put this abracadabra, because I am trying to make a matrix, because for mathematician, matrix is a very important form of form or shape. So, but I am putting a very different kind of matrix. It's a matrix, but in a very different way. This is the matrix for me. Matrix formed from the word abracadabra. Okay, you can see that I have put the word abracadabra here in this matrix form. So you can read abracadabra this way and that way. And the question is, in how many ways can we read the word abracadabra in this matrix? So mathematicians should be able to give the answer. Of course, you can manually do that and go on counting. That will be school mathematics, and we are talking of higher mathematics here. So we'll try to find a solution, or 2-3 patterns of the solution. How to find the solution, to count how many ways can we read the word abracadabra here. So let's try to find the solution mathematically, not manually. But before that, when we teach mathematics, we should start with a very simple example. Similar, but a very simple example. So let me put here something similar. I'll put a matrix very similar over here. Oh, it looks big, but it's very simpler in the same that this word I have put here. Can you guess what I have put here? The word or sentence or phrase over here. here the phrase is like this. In how many ways can we read the word, was it a cat? You can see, you can, somewhere you will see, straight, you can go easily in the straight way. Was it a cat I saw? So, in how many ways can we read the word, was it a cat I saw? It looks bigger one. It looks bigger one, bigger than abracadabra, but this one has a special property. Now, what is that special property? Can any of you guess what is the special property here? Look at this phrase. Was it a cat I saw? This phrase has a very special property. So it is
It's a
called
palindrome. Palindrome.
planetome. Yes, it's a planetome.
I see.
So planetome means you can read from left to right, or you can become a Muslim and read from right to left. It doesn't matter. It gives the same way, same meaning. Was it a cat I saw? So if you read from right to left also, it will give us, was it a cat from, was it a cat I saw? So this is planet. One, it is planetromic. Then the solution will be simpler because this abracadabra is not planetromic. Though it starts with A and concludes with A, but the second word is B and R, not C. So it is not a planetromic. Once it is planetromic, then it becomes more easier. It should be more easier because it has some symmetry. Once you have the symmetry, the solution becomes easy. So without giving any mathematical clue, I'll just say that the total number of possibilities to read was it a cat I saw in that big matrix is 252 square. I'll not say how I got it because my problem is not to give the answer to this. Was it a cat I saw it? But the answer is to abracadabra because my theme is abracadabra. Anyway, so you can read this. Was it a cat I saw in 63,504 ways. Just imagine how large it is. Okay. Now the question is, what about abracadabra? So in half an hour, we'll try to find the answer to abracadabra. Then we'll go to Bernoulli family. Now it has been already said that is a planetome, but this is English planetome. A palindrome is a word or phrase which reads the same in both directions. And very interestingly, words, very simple words, which are very in heart to us, are palindromic. For example, dad is palindromic, mom is palindromic, madam is palindromic. You can say noon is palindromic at 12 o'clock. So these are called palindromic words. There are bigger phrases, just as we have seen here, tie it, borrow or rob, never, add or even. You can go to internet and look at bigger sentences which are palindromic. They are quite bigger sentences which are palindromic. I have put some there, but you can go to internet. A Toyota race fast, safe car, a Toyota is also palindromic. Anyway, but we are interested in palindromic numbers because we are mathematicians. So let's look at palindromic numbers. A number that remains unchanged in value upon writing in its reverse are called palindromic. And very simple numbers are palindromic. For example, 11 is palindromic, 22 is palindromic, all twin numbers or even 1 on 1, 2 to 2, bigger numbers. But I am writing here a bit different type of, I call it special. 121, 1, 2, 3, 4, 3, 2, 1, 1, 2, 3, 4, 6, and so on. So we start with some number, sequence of numbers, and then write the same with the descending numbers. It will turn into a palindromic. So 121 is palindromic, and so these numbers which I have written are palindromic. But I call it special because it has some very nice properties. There are several interesting features here. First is, provided that the highest digit in the conjugative number is even. Here I have put only the even one, you see. 2, 1, 2, 4, 6. You can see here 2, 4, 6, and 8. Provided the highest digit here is even. For such a palindromic number where the highest digit is even, these palindromics are always divisible by 11. All of these numbers, bigger numbers I have written, and you can write even bigger one will be divisible by 11. You can easily see 421 is divisible by 11. Okay. one property. Second property, once you divide by 11, then again you will get back to a new palindromic. For example, this 1, 2, 3, 4, 3, 2, 1. If I divide by 11, you will get 1, 1, 2, 2, 1, 1. It is again a palindromic. So this number, special number, which I have put over here, if you divide by, it is divided by 11, and if you divide 11, you will again come back to a palindromic number. Not only that, if you look carefully at this number, there is a remarkable symmetry to this resulting palindromics. This one, 331. They are made up of a sequence of conjugative digits starting with 1 and with each digit occurring twice. Okay? 1 has occurred twice, 2 has occurred twice, and 11 again has 1 has again twice. Okay. The highest digits in the resulting palindromic, the resulting one, will give us half of what is here. We have 4. Here it will be 2. The highest will be 2, and so on. So if you divide here, you will have 3, 3, something like this. Anyway, so I have called it special, starting with digits increasing and then decreasing, and in the middle we have the even terms. So more on palindromic. Now, if I put these palindromic numbers in this, looking at Pascal's triangle, this is not Pascal's triangles, looking at Pascal's triangle, then it becomes very interesting in the sense that if I add this, if I add these rows, you see, if I add these rows, then it will be square of the natural numbers. It will be square of the natural numbers. 1 square, 2 square, 3 square, 4 square, 5 square, 6 square, 7 square. Okay. How do we find palindromic numbers? Some of them we can easily write it, but can we make palindromic numbers from any number? Yes, we can do that. There is a process known as reverse and add procedure. Pick a number, whatever it is, reverse that number, and write it beneath that first number, or we call seed number. Then add it. Add 2 numbers, you will get a palindromic number. So you will get a palindromic number. If you get a palindromic, voila, or eureka, you have found out the method to find the palindromic number by this reverse and add procedure. Pick a number, reverse a number, write it below it, add it, it will be a palindromic number. Sometimes it may not be a palindromic number, but if you repeat this procedure 1 and 2, 3, definitely at some stage you will come to a palindromic number. So this is known as reverse and add procedure. I will show some example. So 38, reverse it 83, add 121, palindromic number. Let me take another number. So this 38 is known as seed number. Let me take another seed number, 85. Reverse it, 58, add 143. It is not palindromic. You can repeat the same process, 143, I write at 341, add it, 484. Now it's palindromic. Sometimes you have to go down and down. One example, I'll put here, one more example. 475, write 574, add it, you get 1049, reverse it, 9401, you get 10450. It's still not palindromic. Reverse it, 05401, add it, you'll have 15851. So it's palindromic. So this method is called reverse and add procedure, which will give us palindromic numbers. I will only, in small voice, I'll say always, but it's not always. I'm writing one number 1. Looking very simple, 196. This number 196 has a very special name known as list rail number. Do you know this word, meaning of this word, list rail? फटा 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 भन्छ नि हाम्रो नेपालीमा भन्नु पर्यो फटा number. How many times you this reverse and add procedure, you will never come to a palindromic number. फटा भन्छ यताहरु जस्तै for you only. So this number is called literal numbers. There are some other numbers which are not literal, but they are interesting. For example, the seed number 428, 527, 624, all is the same palindromic number with the same number of addition. Okay, so this cluster of number 428, 527, 625 have a peculiar property. So once you go into number theory, you can go for years and you never finish the different type of numbers. Okay. Now, mathematicians are also always interested with prime numbers. So planetronic, among the planetronic numbers, there are some prime also. First planetronic numbers are 2, 3, 5, 7, 11, 101. Not all of them are planetronic. Primes are 2, 3. Of course, here 11 is prime, is planetronic. 101 is prime, planetronic, and so on, so on. So there are certain planetronic numbers among the prime numbers. Number of planetronic numbers less than 10, 100, 1000 are within the 10 you will have 4 only. Within 100 you will have 5, you can count, and so on, so on. Of course, when this prime numbers increases, the planetronic numbers also increases in the pattern I have shown over here. The currently largest known planetronic prime has 39,027 digits and was found by Hervé Dubner in 2001. Of course, after 2001, I have not searched it. By 2021, there may be bigger planetronic prime number. I am still not aware. You can go to internet and look at it. Because I have borrowed this slide from 2004, so that's why I can put only data up to 2001. And that planetronic number is such a big number, which I can't put here. It's 39,027. I can't even write in this computer here. Now coming back to our problem of finding how many, in how many ways you can read abracadabra in this strange type of matrix. Before that, as I told, I should start with a very simple one. Just suppose it's a well-planned city with square blocks and straight lanes, just like in New York, similar to New York. So let's try to see how this will help us in finding in how many ways you can read the abracadabra. So I'll put abracadabra in the corner of this well-planned square block and straight line city. So A I have put here, abracadabra. Okay. Abracadabra here. For example, and you finish. So one way you can read like this. That means you can start from this A corner and read this A commit along this road. Okay. Of course, there are so many zigzag roads here. Now, to make it mathematical, let's look at the left vertical lines, left slant lines. Okay. So that means now the problem will be find the number of shortest routes between these two corners A and A. So if you would count the shortest route from this A to this A, you will be able to find in how many ways you can write, read abracadabra. Okay, so now I have changed the problem to this finding the shortest route. There are many algorithms to find the shortest route. Now, before finding the answer, let me look at this. Now, this is familiar to you. This is Pascal's triangle. I have put a Pascal triangle. Instead of abracadabra, I have put a Pascal triangle. Okay, here you can see I have put Pascal triangle. Now, starting from A, if I somehow come to A somewhere here, which will be somewhere here, and looking at this Pascal triangle, maybe we will be able to solve it, because now I have somewhere to go. Because from here up to here, you can read by two ways. It says you can either go like this, either go like this. So if you to reach this here, you can go like this, you can go like this, you can go like this. There are three ways. So this has now giving clue to finding the shortest route here using Pascal triangle and putting the values of Pascal triangle in this pattern of square blocks. Okay. This is really familiar. This is Pascal triangle. Yes, this is Pascal's triangle. So now we'll use it. But before use it, giving the real answer, look at a small word catch. C-A-T-C-H, catch. Not palindromic. So let me put it here. I'll try to catch, not it is not a phrase over here. Let me catch it. From here I'll count it. Now if you count it here, then you can see that I'll put it in the format of the Pascal triangle now. Okay. Pascal triangle here, 1, 1, 1, 1, 2, 1, 3, 3, 6. So then this edge, this is now 6. This 6 will give us the answer. So catch in this small matrix can be read in 6 ways. Let me show all these 6 ways here. Let me show all these 6 ways here. Okay, 1 way, 2 way, 3 way, 4 way, 5 ways, and lastly 6 ways. So Pascal triangle is so much useful. Now with this idea, now I have the answer. We have the answer. So for this abracadabra, the answer is 252. Okay. So the answer to the solution is 252. You can read abracadabra in this strange type of matrix in 252. But when we had this palindromic you can read this way from top to bottom and bottom to top. So you read 252 square. That is what it was written here in the answer in the case of that's palindromic. Okay. So that was one solution. So one solution to find in how many ways we can read abracadabra is by using the Pascal triangle. So that means it's an application of Pascal triangle. Mathematicians always try to find another approach. Let me try to find another approach. So let me use this same diagram here. Oh, okay. What I'll do is just slant it. This slanted. Let me indicate by L, and this other slanted, 90 degree other slanted by R. So L is not only this one. L is this 3, 2 here. Where I have 1 here, I have 2 here, and R is just so much here. Okay. Yeah, so done. R is all this one here. So this inclination is denoted R, all inclination denoted by L. So in this format, in this case, you will see that N is of course 10. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 steps. And this way is 1, 2, 3, 4, 5. Okay, this side is a 1, 2, 3, 4. 1, 2, 3, 4, and 5. So R is also 5 in this case, L is equal to 5. And then, of course, this one is then the combination of N. We have to find combination of 10 taken 5 at a time is 250. Of course, it will give the same Pascal triangle. Yes. So by using this root also, you can find the value 2. There's a number of ways in which we can count abracadabra. Now, since we have seen that Pascal triangle is so useful, let's have some study on Pascal triangle. We can write now from this one by combinatory systems. You can write Pascal triangle in this format. C0, 0, 0, C1, 1, 0 from 1, 0 from 1, and so on. And this is called this on this left and on the right are called boundary numbers. These are all value 1. They will give us value 1. Others is the sum of the at21. And so, and the row are 0, 1, 2, 3, 4. And then we can write this value. So this will, you can see this is the 4th row. The position here, 0 position, first position, 2, second, 4, 3, and 4, and so on. And we know the recurring formula for Pascal triangle. C n plus 1 taken R at a time is equal to C R taken out of n, C taken out n taken R minus 1. So recurring formula, very similar to what we saw last time, even as in of course, this C n of R is given by the expansion formula. Expression formula to find the variable coefficients, we know that. Pascal triangle are the coefficient of diagonal expansion. In Pascal form name this Pascal triangle, then let us see how Pascal proved this formula in his time. I don't know how we prove the formula right now. So when it r is equal to 0, then we have Rn1 which is 1. And when r is equal to some value n, then we have this formula which I have just written over here, this formula. And if you put n plus 1, Rn minus 1, just before that, it is r, and just before that, you have it. Now, if you go one step further, if you add these two, then you will have, using this second formula, you will have n plus 1, then you will get this formula. And this, you will say that since it is correct for n is equal to 0, we have seen that it is correct for n plus 1, we have put the correct. So correctness of formula for n implies correctness for n plus 1. This is called induction method. So Pascal proved this formula for the expansion of this combination using what is known as the induction method in this time. I have shown this earlier also, but it is very interesting. If we add up the sum of rows of elements of this Pascal triangle, you will have again 2 to the power 0, 2 to the power, 2 to the power, 2 to the power 3, 2 to the power n, and so on. And it's very useful for people who are studying computer, because computer always works with 2 to the power, because it's a binary system. The first element in a row is a prime number. All the numbers in that row are divisible by it. Okay. If a diagonal of numbers of any length is selected starting at any of the bordering stars are 1, the triangle and ending any number inside the triangle on the diagonal, the sum of the numbers inside that selection is equal to number just below the end of selection. I'll show it. It's called a hockey stick. It will be for the shape is like this. You can see. From here to here, the sum will be 84. From here to here, the sum will be like this. Yes. So this is called, this is a hockey stick. 1 plus 12 is equal to 30. Yes. 1, 6, 21, 56, 84, and so on. So Pascal triangle are very interesting properties. I am going to show only few other things to deal with. A row is made into a single number by using each element as a digit of the numbers. Carrying out over when an element itself has more than one digit. Number is equal to 11 to the nth power of 11 to the power here. When s is the number of a row in the multi-digit number are taken from. So, see this one row is 14641. So, if you instead of writing 1461 as separate numbers, if you take it as a number, whole number, one number singular 1461, it will be 11 to the power 4 because it is fourth row. Okay, fourth row. And this bigger one, below it will be 1510 1051. And if you take as a number, I should write it as a 1 because 5 and 1 will sit, and 0 is there. Here also 5 and 1 is, and so 5 1. So 11 to the power. So there are some interesting, a lot of interesting at the figure below, because for students, geometrical representation or diagrammatic representation is always interesting. So I am writing here numbers in this format, 6 and so on. Just like packing the cigarettes. Okay. So these are Pascal triangle. These numbers 1, 3, 6, 10 are from the Pascal triangle. Okay, I'll show it again in the Pascal triangle. So these are from the Pascal triangle, and it is here 1, 3, 6 in this diagonal, and these numbers are called the nth triangular number. This number is called the triangular number. It's called the triangular number. 1, 3, 6, 10, because we start with, you can see it's a triangle form. 0, of course, 1 is. Here is that, you can see, but it's a triangle form. It was all in the triangular form. a triangular form, bigger triangle, bigger triangle. So that's why this number 1, 3, 16 are called the triangular numbers. These are called the triangular numbers. These are called the take up to n, it will be called n triangular number. So 1, 3, 16, 15 are triangular numbers. If you move down, you will have 1, 4, 10, 20, 35, and 56. Move down. This has another name. Another name called pyramidal numbers. So it's C22. I'm taking the elements C22, C32, C42, and so on. That is, they are called the pyramidal numbers. I was making a summary. Triangular numbers and pyramidal numbers were known long before the binomial quotients were conceived. Now, if I put it as summary, Fibonacci number also looks very similar. Fibonacci numbers. So put the nth member of the Fibonacci numbers. So here, the recurrent formula is like this, which we know. And so the Pascal's triangle, in the Pascal's triangle, we can again find here inside the Pascal's triangle. If I look in this slanted way, you will again find 1 plus 2 is equal to 3, 1, 3, 1 is equal to 5, 1, 4, 3 is 8. So here you can see we are getting the Pascal's, from the Pascal's triangle, we are getting the Fibonacci numbers. So Fibonacci numbers then is related with Pascal triangle because Pascal triangles are formed from the binomial coefficients over here. So the relation is Fibonacci number is elements taken sum of these. Okay. We have to add 1 here and deduce 1 here. Add 1 here, deduce 1 here, and that will be the Fn taken with the help of Pascal triangle. If you would rotate more, so I have written, you can rotate more. If you rotate more from this Pascal triangle, here 1, 1, again 1. And 1 plus 1 will give us 2. 1 plus 2 will give us 3. Putting so okay, so 1, 4, 1, 3, 4, and so on. This is in 1, 1, 2, 3. It's not Pascal number. So you can go on rotating. Sequence form we have some is here 1, 1, 1, 2, 3, 4, 6. It will be something like this one. This denotes the nth member by Gn. Then we can also have a recurring formula Gn. You can see that recurring formula is something like that. Okay. 1 here and 2 jump over here. 1 here and 2 jump over here. So Gn by Gn minus 1. Okay. And then Gn minus 3, you have to go back to. If you want to find the 6, you have to go back 4 and 2 more steps back will be 2. 2 for 4 plus you will give us 6. Now I am not writing here, I am not giving you. You can find the expression for Gn in terms of binomial coefficients. I am leaving as footnote. Now put it all in a summary for this Pascal triangle, but here I have put the Pascal number in what is known as left justified Pascal number. Actually, when Pascal started introducing this Pascal triangle, actually his triangle was like this right angle triangle. It was left justified Pascal triangle. Now you can see that here it is on the these are the edges 1 on 1. Then this one will be natural numbers. This one is triangular numbers, which we have seen. This is called tetrahedral numbers over here. This number 1, 5, 15, 35, 7 are called pentatope numbers. Here. And this one 1, 6, 21, 50 are called 5 simplex number. This one is called 6 simplex number. This one will be called 7 simplex number. So and so and so on. So in Pascal's triangle, if you write it in this left justified Pascal triangle or in the right angle triangle in the shape of right angle triangle, then you have this type of formula. Do you know what is simplex? Simplex means all geometrical shapes with the triangle, tetrahedron, pentahedron, and so on are in a set form is known as simplex. Anyway, we have not heard about this word. Now, that's enough for abracadabra, because with abracadabra, I can do many, many things. But since we are talking of history of mathematics, then I should also uh, give some contribution on one of the, I'll say, the most strong mathematics family in the history of mathematics, and it is known as the Bernoulli family. So, contribution of, I'll try to give short contribution of Bernoulli family to mathematics. There are some of the Bernoullis over here. So, look at this family tree of Bernoulli family over here. So, it starts from Nicholas Bernoulli, and he has 3 children. Here he has only one child, but this Jonas Bernoulli has 3 children. This Jonas second Bernoulli has another 3 children, and so on. Of these 3, 4, 5, 6, 7, 8, 9, 10, 11. Of these 11 family members in 3 family tiers, generation, these 8 people are great mathematicians. So Jacob Bernoulli, Johann Bernoulli, Nicholas Bernoulli, Nicholas second Bernoulli, Daniel Bernoulli, Jonas second Bernoulli, and Jonas third Bernoulli, and Jacob second Bernoulli. They are all mathematics. Others are more related to medicine rather than mathematics. So you can see a family with 8 prominent mathematics is a real family which has contributed to mathematics. Starting from, you can see that 1600 or to 1700, from 17th century to 2 centuries. So they have contributed here. So that's why it is very important and necessary to talk about this Bernoulli family. And there is some other, my personal interest also here when I am talking of this Bernoulli family. With that interest, we will come later on. Bernoulli family was originally from Poland. All of Bernoulli mathematicians were descendants of Nicholas Bernoulli, as I have shown over here, a prominent merchant in the spice business, Maslako Vyapar, in Basel. Though they were from Poland, but they had a business in Switzerland, in Basel. I visited that city, Basel, in 2019, recently. And so they came as a business people in Basel and then settled in Switzerland, Basel. Within 3 successive generations, the family produced as many as 8 mathematicians who contributed vastly to the mathematics world. And so, in which field of mathematics they have contributed. Among the 8 Bernoulli mathematicians, the most famous among the 8 are all spanning 3. Out of 8, 3 are really prominent ones. They are Jacob I Bernoulli, Johann I Bernoulli, and Daniel Bernoulli. There are two Daniel Bernoulli in the family. In the third generation also, there is one Daniel Bernoulli, which is not a mathematician. Only the second tier is Daniel Bernoulli from 1790 to 1790. So I have marked here these 3. You can see here is another Daniel Bernoulli. He is not a mathematician. Only this Daniel is mathematician. So this Jacob Bernoulli, 1664, 1705, his contribution is on differentiation and integration, calculus of variation theory, and he has a special number called as Bernoulli number given by this formula over here. This Bn is known as Bernoulli formula. And then second is Johann Bernoulli. So he is the starter of what is known as Pascal's rule, differentiation and integration again. And very prominent, famous problem is called Rice-Stokes-Krohn problem, about which we will talk in a later page over here. Other most prominent one is Daniel Bernoulli, who contributed in Bernoulli laws, and he has a polynomial known as Bernoulli polynomials. Yeah. So these are such a prominent mathematician. That's why we have to talk about this Bernoulli family. Coming back now, 3, we'll talk about this 3. One Jacob I Bernoulli, 1654, 1705. Jacob Bernoulli is the oldest son from the topmost Baje, Nicholas Bernoulli. He was first in the family to be recognized as a strong influential mathematician. He has published 5 treatises on infinite series between 1682 to 1704. in May 1960, 1990, he published a paper in Acta Eruditorium that was a very famous mathematical publication at the time, and showed that the problem of determining the isochrone is equivalent to solving a first order linear differential equation. So he has tried to link practical problems with mathematics, especially with differential equations. The isochrone, also called curve of constant descent, very interesting curve. The isochrone called curve of constant descent is the curve along which a particle will descend under gravity from any point to the bottom in exactly the same time, no matter where it starts. Let me show physically this one. You can see if you start from here, it will come to this point at the same time. If you start from here, it will also come to the same point at the same time. This is known as isochrone. Jacob Bernoulli was the first mathematician to use the term integral calculus. So, we as a historian talking about the history of mathematics to learn that Jacob Bernoulli was the first person, mathematician, to use the term integral calculus. In May 1960 issue of Acta Eruditorium, which I have already told, Jacob wrote, and now let this problem be proposed to find the curve assuming by a loose string hung freely from two fixed points. 1 year after the appearance of this problem, in the June 1920 issue of Acta Eruditorium, 3 correct solutions were published. The 3 solutions came from Huygens, Leibniz, and Johann Bernoulli, his younger brother, also gave a solution. He is also an honor prominent man. Although they approached the problem from 3 different points of view, all of them conclude that the curve would be a catenary. Jacob himself failed to solve the problem. He gave the problem, but he didn't solve himself. Only his younger brother. The catenary equation of the Cartesian equation of a catenary is given by its equal to power x plus minus x. There is a constant whose value depends on the mass per unit length of the chain and the tension of the suspension. So, something like that. Form like this. Jacob Bernoulli was one of the pioneers of the mathematical theory of probability. His first paper on probability theory was published in 1685. The greatest contribution of Jacob Bernoulli in ars conjecturae, the art of conjecturing, contained many of his finest concepts. His theory of permutation and combination, the so-called Veruli numbers, by which he derived the exponential series. This treatment of mathematical and moral predictability, because probability predicts something, and the subject of probability conjures what is now called the Bernoulli's law of large numbers. This law of large numbers was a very vast mathematics, basic to all modern sampling theory. And Bernoulli numbers are like this one. The sum of kth power of first n natural numbers, very simple. First k natural number is denoted by skn is equal to 1 to the power k, 2 to the power k, sum of kth power of first natural numbers. So k is equal to 1, k is equal to 1, we'll have 1, 2, 3, sum of the natural numbers. Sum of natural number, the formula we know. If we put s is equal to k is equal to, we'll have sum of the square numbers. So we can compute skn, general formula, by using this very speaker formula. So S2n is sum of over here. You can write it in compact form over here. Just like we have written for S1n, n plus 1 by 2, we can write S2n. That formula is something like this. S3n is like this, and S4n is like this. And noted it over here. And so you will see after some time when you come to here, it's all summation over here. So the kth Bernoulli number Bk is the quotient of n in skn. For instance, B0 is quotient for Sn in S0n, which is n. And so B0 Bernoulli number is 1, B1 will be minus half, B2 will be 6, 1 will be 6. So there is no sequence over here. It's very difficult to predict this, what is known as Bernoulli numbers. Some properties of Bernoulli numbers, for odd k is equal to 0, dq will be 0. And for even, you can see, for odd it will be all negative like this. This approximating for all k greater than 1, dq will be 0. For all k is equal to greater than 1, dq will be 0. For even k will not be equal to 0, so it will be something like this. 0 is 1 is the only 0 non-zero integer, others will be plus minus over here, and so I'm not going to read this. Now, anyway, this Bernoulli family numbers are very interesting numbers. So Bernoulli numbers are used in differential topology and so on, and analysis in modern forms in different homotopology theorem, number theory, and in polarization and so on. So it's very important number. Now coming to Jacob Bernoulli. His contribution was twofold. Bernoulli trials are essentially coin flip repeated many times, probability theory. Toss a coin, your coin 10 times, and you might get 6 heads and 4 tails rather than and exactly 5 by 5. So his contribution is in probability. Toss 100 times, and you can quite unlikely to get 60 heads and 40 tails. The more times you toss the coin, the closer you will get to 50-50, which we know that. That is why we have to do a lot of experiments, because before you make a conclusion. Bernoulli's golden theorem, again printed in Ars Conjectura. This is therefore the problem that I now want to publish here, having considered it closely for a period of 20 years. So he worked for 20 years on this problem. And it is a problem of which the novelty as well as high utility, together with this grave difficulty, exists in weight and value of the remaining chapter of my doctrine. So this is the problem which I pose over here. To illustrate this by example, I suppose that without their knowledge, there are concealed in an urn 3,000 white pebbles and 2,000 black pebbles. And in trying to determine the number of these pebbles, you take out one pebble one after another, each time replacing the pebble you have drawn, because it again goes back to 5,000 and over there. And you observe how often a white and how often a black pebble is withdrawn. So this is experiment you like to perform. The question is, can you do this so often that it becomes 10 times, 100 times, 1,000 times it is more probable than the number of whites and blacks chosen are in the same 3 to 2. Because you can see 3,000 pebbles, 2,000 black means it is in the 3 to 2. And after you draw and write down all this you have drawn down, can we say that it will be in the ratio 3 by 2? So this is the problem here, posed over here. Jacob also showed special interest in the logarithmic spiral, which was introduced in 1637 by René Descartes. At this time, the polar equation of the curve was written as r to the power e to the power a cube, where q is measured in radians and a denotes the rate of increase. So this is the spiral over here, known as logarithm spiral. Jacob Bernoulli was so astonished by this magic of the logarithm spiral that he requested to have a figure of a logarithm spiral engraved on his tombstone with the word "Edem mutata resurgo," changed and yet the same, because the spiral looks changing, but it is again the same. So I rise again. So in his tomb, this is engraved in his tomb. Now coming back now to another, Joan Bernoulli. Joan Bernoulli was Jacob Bernoulli's younger brother. He was a brilliant mathematician who made important discoveries in the field of calculus. He asked his brother Jacob to teach him mathematics. With Jacob's help, Johann studied Leibniz's papers on calculus until he became proficient, and his mathematics prowess soon matched that of his brother. Actually, he became more prominent than his brother. So there were even some fighting over there. That is logical fighting or knowledge fighting. Bernoulli's brothers were among the few mathematicians in Europe to understand calculus. So at a time in 17th century, these people, Bernoulli family, knew mathematics more than other mathematicians, of course, and of course not more than Leibniz. They are guru. Johann was perhaps even more productive as a scientist than Jacob. So this younger was more productive than senior. After Newton's death in 1727, Johann Bernoulli was unchallenged as the leading mathematician preceptor to all Europe. Since his return to Basel in 1705, he had devoted himself in the field of applied mathematics to theoretical and applied mechanics. Johann Bernoulli's quarrelsomeness was matched by his passion for communicating. His scientific correspondence comprised about 2,500 letters exchanged with some 110 scholars. You can see, even in those times when they didn't have internet, they didn't have other big postal service, but he has different ways of making correspondence. So that was the nature of Johann van Bernoulli. And he posed this Reichstochrome challenge. He said that I, Johann Bernoulli, is the most clever mathematician in the world. Nothing is more attractive to intelligent people than an honest, challenging problem whose possible solution will bestow fame and remain as a lasting monument. Following the example set by Pascal, Fermat, etc., I hope to earn the gratitude of the entire scientific community by placing before the next mathematician of our time a problem which will test their methods and strength of their intellect. If someone communicates to me the solution of the proposed problem, which is going to propose now, I shall then publicly declare him worthy of praise. So that is the challenge given by Johann Bernoulli. This Blackstone challenge was given on January 1, 1697. So what is that? The problem is like this. Let's perform an experiment here. Let me physically perform an experiment here. So you see, of these three balls starting from the same time, this one in the blue arrives at this point quicker than the two arrives at the same time, but this one arrives very quicker than the fixed. Now the problem is to find this curve of quickest descent. That is what is known as Ratchet-Chrome challenge. To find the curve with the quickest descent. This curve is cyclide. Now, we'll talk about that problem later on. Now, coming to Daniel Bernoulli, 1700-1782. Of these three prominent mathematicians in the Bernoulli family, Daniel Bernoulli was the most gifted son of Johann Bernoulli. He loved to study mathematics problems, and he published his excursion mathematics exercises in Venice in 1724. At the age of 25, he submitted his work to the annual contest of the Paris Academy and won the Grand Prix prize. Between 1725 and 1749, Daniel won 10 prizes from the Paris Academy of Sciences for work on astronomy, gravity, tides, magnetism, ocean currents, and the behavior of ship at sea. So you can see what a big contribution. Relation between Johann and Daniel became strained when in 1974 they both competed for the grand prize of the Paris Academy, the School of Mathematics and Physics Sciences. They both won, and the thought of sharing the prize, which is one son, sent Johann into a rage. So they both got the prize, and they have to share the prize. It was won by both of them, and the father didn't want to share with his son. So there was a conflict between. So he banned Daniel from his house. So the father sent the son Daniel outside his home. Johann Bentley categorized hydrodynamics in his publication of Hydraulica, and even made it seem as if his work was published first by backdating it to 1732. The plagiarism, however, was soon uncovered. You can see this tendency of plagiarism is not in the 21st century. It was there in the 18th century itself, even between father and son. So this is the hydrodynamics. In his later years, Daniel Bernoulli continued to work in calculus, mechanics, conservation of energy, oscillations, and the movement of bodies in a resisting medium. There is a Daniel from Nepal also. There is Daniel from Nepal. So I want to show His name is Daniel Tuladhar. This is Daniel from Nepal. Daniel Tuladhar has a master's from Kharkov Highway Engineering Institute from Ukraine, and he has PhD from Kursk State Technical University, Russia. Currently, he is the head of department, mechanical engineering department at Kathmandu University, and proudly he is my son. That's why I said with Bernoulli family, I have a very strong connection. So my son's name is also Daniel. So when he was born in Dharan in the British hospital, British Camp Hospital. So I wanted to give him a special name. So I have this book on Bernoulli family. Then among the family of Bernoulli, the most convenient name for Nepali was Daniel. So I gave him name as Daniel Tuladhar. So now he's also a big man. He is the head of department. He has a PhD from Kursk State Technical, very highly qualified university in Russia. And you see, here is another photo. This is his brainchild making a racing car, prototype racing car at Kathmandu University Department of Mechanics. These are the researchers and students of Kathmandu University Mechanical Department. So with his help, so they have designed this car, and it was taken into Malaysia for competition in the Grand Prix racing, what is known as this racing track. So this is in the racing track in Malaysia, the Grand Prix. Over here is a prototype made in Nepal at Kathmandu University. You can see how Nepali engineers are also very prominent in making such nice car over here. So it's made in Kathmandu University. Now coming back to this brachistome challenge, we suppose that a particle of mass m moves along some curve under the influence of gravity. We'll assume motion in 2 dimensions here, and the particle moves starting at rest from fixed point to a fixed point B. The question is, what is the shape of the curve for which the time to get from A to B is minimized? So that's what we mean by brachistome. So I have already shown the experiment. I am showing again. So to find this blue, what is this curve? This curve is sine phi. The equation of the motion will be given from this over here. So I'm quickly showing over here. So we use the calculus over here. So about calculus we'll talk only next time. But since it is a simple matrix, I am showing it quickly. So this was actually drawing in his handwriting, which I have from Newton to solve this problem in 1697. I have taken it from his book over here. So I'm going quickly because there's simple mathematics. You can go home and look at the slides and then look at the mathematics. I'm not going to teach mathematics here. I'm going to teach history of mathematics only. Anyway, so it will be something like this. Parametric equation of inverted saccharoid is here. So here. And you can easily see that is that I'm showing the mathematics. It's not interesting to show all this mathematics. You can read it. And most of you are good mathematicians. And I'm not going to read it. Here in the slide, you can use it. As I say, I'm not teaching you mathematics. But now, coming back, the last time when I left it, I said, believe it or not, if you convert a square into rectangle, the area is increased by 1 unit. So it was over here, this 1 has come over here, this 1 is 1, this 3 is over here, and 2 has come over here, this 2 big triangle, 4 has come over here. Now, this is 8 into 8, this is 5 into 13 into 5 equals 65. So one area is increased, something has mismatched. Now I'll just give you a clue why it is here. I don't know whether how you have got it. Now here you see these 2 triangles, 2 and the bigger triangle 2 plus 4. This 2 and 2 plus 4 together. They are what is known as congruent triangles. Okay. So the ratio will be 8 by 3 here. And this bigger triangle 2 plus 4 is this triangle. It is 13 by 5, 13 by 5. So if this small triangle and this whole big triangle is congruent, then their ratio of the sides should be equal. But what we are finding here is the ratio of sides are not equal. It's 8 by 3, it's like 13 by 5. They are not equal. So if you want to make equal, then you have to make simple, same denominator. We put the same denominator. Yeah. Here it is 40 by 15, 39 by 15. So it's not mismatching. Some mismatching is here. So you have to see what is mismatching. My idea was most probably by this making a longer diagonal, one unit has been increased. So these are the reference over here. I have taken over here. A book of Bernoulli and other references over here. Now, since I am showing here this book, the Calculus Gallery, so my next presentation, the seminar will be on moment pencil. And since I am using that book, so I will be talking about the Calculus Gallery next time, X7, mathematics theory. Okay, that will be enough for today. So there are a lot of mathematics which I am not telling you in detail. You are mathematicians, you can read for it. And since I will be sending the PDF file, then you can read. Okay, thank you very much. Yes, sir. अलिक छिटो गयो मलाई
होइन सर मलाई एकदमै मैले त इन्जोय गरिरहेको थिएँ सो दीपक सरले बिचमा केही ह्यान्ड रेज गर्नुभएको थियो सर केही क्वेसन थियो
मेरो खै त्यो अटो प्रेस भएर त्यस्तो बिचमा त केही क्वेसन थिएन तर अहिले गर्न मिल्छ भने गर्नु पर्यो खासमा त त्यो पालिन्ड्रोम नम्बरदेखि अगाडिदेखि सबै ट्र्याक गरिरहेको म भर्खर मेरो 8 मार्क सकेन अनि सरलाई रिपोर्ट गरिहाल्नु 5 माइल 8 किलोमिटर I was running, I still breathing उस भइरहेको छ खास चाहिँ त्यो मलाई इम्प्रेसिभ लागेको चाहिँ सरले त्यो बर्नौली फ्यामिलीसँग चाहिँ
एक प्लेट ब्रेक गर्नु एक प्लेट ब्रेक गर्नु अब
Good madam. Can I ma'am हुनुहुन्छ त्यहाँ
एकैछिन सर वाशरुम जानुभएछ
त्यही मौका छोपेर चाहिँ घना म्यामसँग गफ गर्नु भने म्याम हराउनु पर्छ
साइलेन्स भयो त सर कति जानुभएछ
त्यही भनेर म्याडमलाई सोध्दै थिएँ के छ म्याडम हालखबर आजभोलि
एकदम ठिक छ यस्तै टक्सहरू सुन्ने अनि अलिकति रिभाइभ गर्ने म्याथमेटिकल वर्ड टर्म्स डेफिनेसन्स थ्योरम फ्यामिली
ओनिम्स के गर्दैछ अनि
एकदम राम्रो गर्दैछ अनि अब गर्नेवाला छ गर्ने प्रयासमा छ त्यस्तै छ के गर्ने के भन्नु
यो नेचर स्कललाई रोक्नै सक्छ
सर आउनु भयो फेरि कुरा गरौँ है सर आउनु
त्यस्तो खासै सिरियस क्वेसन त केही छैन म्याथमेटिक्स चाहिँ पछि त्यो बर्नौलीको कुरा आइसकेपछि चाहिँ अलि फलो गर्न नसके जस्तो भयो अब त्यहाँ चाहिँ लुक्स लाइक अ लट अफ म्याथमेटिक्स त्यहाँ
भन्दाखेरि कसो चाहिँ त्यो कसरी चाहिँ डिड्युस गर्यो भने इन्ट्रेस्टिङ हुनसक्छ त्यो पिडिएफमा हेरे हुन्छ होइन त्यो म एक्सप्लेन गर्न आइ एम नट गोइङ टु टिच म्याथमेटिक्स मैले भने आइ एम नट टिचिङ म्याथमेटिक्स टाइप म हिस्ट्री पढाउनु खोजेको हो तर त्यो बेलामा नै चाहिँ म्याथमेटिक्स कति मजासँग चाहिँ अरू म्याथमेटिक्सहरूलाई युज गरेको छ भने त्यो देखाउनलाई राखेको
तर अब जस्तो अब आई मिन भेरी नाइस कनेक्सन विथ द हिस्ट्री अफ म्याथमेटिक्स अनि त्यो नम्बर थ्योरी धेरै जसो त्यो देख्नु पाइयो कि अनि म अहिले मिडल स्कुल टिचरलाई पढाउँछु कि अनि उनीहरूलाई पनि नम्बर थ्योरी बेसिक नम्बर थ्योरीहरू पढाउँछु हिजो मात्रै एउटा असाइनमेन्ट दिएको थिएँ बाइनोमियल एक्सपान्सन पावर 7 राखेर अनि त्यसमा त्यो पास्कल ट्रायङ्गलदेखि लिएर सबै कुराहरू आउँदाखेरि कस्तो रिकल भयो जस्तो चाहिँ फिल भयो तर जस अनेस्टली आफ्टर हाफ पार्ट पछिको म्याथमेटिक्स फलो गर्न चाहिँ एकछिन बस्नै पर्ने जस्तो रहेछ
बसेर हेर्नुपर्छ मैले भनेर बुझेँ कि चाहिँ मैले त्यसको लागि एक क्लासै लिनुपर्छ बोर्डमा राखेर अथवा चाहिँ कुनै त्यो राखेको र व्हाइट बोर्ड राखेर होइन त्यसपछि त्यो कसरी डिड्युस गरेको भनेर एकपछि डिड्युस गरेर पनि एक्सप्लेन हुन्छ त्यसैले अब भोलि पिडिएफमा मजासँग आफै गएर घरमा आफैले होमवर्क गरे हुन्छ अथवा चाहिँ रफ वर्क गरे हुन्छ तर तर क्यालकुलेसनबाट कसरी त्यो इक्वेसन निस्किन्छ कुन फर्मेटमा निस्किन्छ भने त्यहाँ राखिदिएको छु। सो त्यसपछि चाहिँ उत्साह जाग्छ भनेर हिसाब गरेर
भेरी नाइस। सरले अनि छोराको नाम त पुरै बर्नौलीहरूलाई डेडिकेट गरेर राख्नु भएछ त अनि
होइन अब मौकै त्यही पऱ्यो त्यही अनुसार नराखेपछि के हुन्छ मान्छेलाई चाहिँ नि त्यही अनुसार काम गर्नलाई चाहिँ नि जागर पनि हुन्छ जस्तो लाग्छ मेरो। ड्यानियलको नाउँ राखेपछि ऊ पनि ठुलो मेकानिकल मान्छे नै हो होइन त्यत्रो कार बनायो मलेसियामा रेस गर्न सक्यो। त्यो युनिभर्सिटीको च्यालेन्ज प्रब्लम थियो कि त्यो हाम्रो मात्रै होइन त्यहाँ 5-6वटा युनिभर्सिटी मलेसियाको पनि थियो अरू देशहरू पनि त्यो त्यस्तै चाहिँ विभिन्न खालको कार बनाएर ल्याएको थियो। त्यो स्टुडेन्ट लिएर गएर यहाँ पहिला प्रोजेक्ट गरेर बनायो कार होइन प्रोटोटाइप बनायो रेसिङ कार लयो।
वाउ इन्ट्रेस्टिङ मजाको। अहिले त अनि त्यही काठमाडौँ युनिभर्सिटी नै हुनुहुँदो रहेछ है मलाई थाहा थिएन। गजब गजब गजब। धना म्याम के सोध्न खोज्दै हुनुहुन्छ?
मलाई एकदम इन्ट्रेस्टिङ लाग्यो सरको एकदम सरल र मैले आज फर्स्ट स्लाइडदेखि नै बस्न पाएँ कि अनि एकदम सरल र गइरहेको थियो। सरले एक्ज्याक्टली भन्नुभयो कि व्हाइट बोर्डमा पढ्न पाएँ हामी कस्तो एकदम म्याथमेटिकल हिस्ट्री म्याथमेटिकल टर्म्स डेफिनिसन्स अनि म्याथमेटिसियन्सहरूले गरेको कामहरूसँग सरले एकदम कनेक्सन गरेर जुन लास्टमा त म्याथमेटिक्सको बर्नौलीजको फ्यामिलीबाट आएपछि त थ्योरम इक्वेसन प्रिन्सिपल नम्बर्स के हो यो बर्नौलीजले जुन डेभलप गरेको छ नि त्यस्तै म्याथ फ्यामिलीको पनि छ। सरको यहाँ चाहिँ यसरी के व्हाइट बोर्डमा पढ्न पाए त एकदमै झन् अझ इन्ट्रेस्टिङ हुन्छ जस्तो लाग्यो मलाई। क्वेसन पनि बिचमा रेन्ज गर्नुपर्छ जस्तो सरले पास्कल ट्रायङ्गल देखाएर सरले जुन आब्राकाडाब्रादेखि पास्कल ट्रायङ्गलदेखि सरले सिक्वेन्समा आएर अनि रिकर्सिभ फर्मुला पनि देखाउनु भएको थियो नि जिएन इजिकल टु जिएन -1 प्लस जिएन +1 त्यहाँनिर चाहिँ कन्फ्युज भयो। त्यसपछि त म कहाँ हराएँ क्या सर। तर सरले जुन एक्ज्याक्टली त्यो बुझ्ने कुरा त होइन पढ्नु नै पर्छ। अब एकदम इन्ट्रेस्टिङ चाहिँ छ।
एउटा टपिक एउटा प्रोब्लममा मैले लेक्चर दिएको होइन यो ब्रोडमा गरेको जस्तै चाहिँ मान्छेहरूलाई यस्तो चिज पनि हुन त कोही हेर्नु पर्यो खोल्नु पर्यो भनेर मान्छेहरूलाई चाहिँ उत्साह जगाउने
मोटिभेसनल छ सर। अनि त्यहाँ जिएनमा आउँदा त मैले त जिएन +1 नभएर जिएन बराबर जिएन -1 प्लस यान हुन्छ जस्तो लागेर अनि सरलाई मात्रै त्यो एउटा जिज्ञासा मात्रै भनेको।
स्टेपबाट जानुपर्छ।
हजुर थ्याङ्क यू सर। त्यति हो मलाई एकदम खुसी लाग्यो। अब बसेर यसरी सुन्न पाउँदा पनि राम्रो के अरे आफू हामीलाई पनि अलिकति
मेरो सबै टकको कामहरू यस्तै चाहिँ किसिमको हुन्छ जसले चाहिँ अलिकति म्याथमेटिक्स स्टार्टिङ फ्रम नेचर नट इट्स इमेजिनरी नम्बर इमेजिनरी फ्रम इमेजिनेसन।
दीपकसँग पनि भेट हुन पाएँ आज।
अरूको चाहिँ नि टु मेनी म्याथमेटिक्स डिसिप्लिन भए पनि मेनी अफ देम आर सम वे इन्टर रिलेटेड भन्ने पनि म देखाउनु खोज्छु।
हजुर थ्याङ्क यू सर।
अनि म जस्तै अरू पनि जागर होस् सबै ठाउँमा चाहिँ नि पुगेको होस् सबै काम गरिरहेको होस् भनेर तपाईँहरूलाई चाहिँ घचघचाइरहेको हुन्छु कि म। मेरो हरेक प्रेजेन्टेसनमा एउटा दुईवटा मेरो स्लाइड चाहिहाल्छ हाउ आई एम रिलेटेड विथ म्याथमेटिक्स। Any more question? अब मेरो त्यही चाहना छ 5:30 बजे भनेको 5:30 बजे नै भनौँ न 5:10 मिनट 40 भित्रमा सुरु गरिरहेको छु हामी अलिक राम्रै चाहिँ टाइममा सुरु गर्न पायो भने बिस्तारै भन्दा पनि मैले सही हुन्छ ढिलो गर्नु नहोस्।
त्यही नै हो सर। अनि अर्को चाहिँ यो हाम्रो अब पार्टिसिपेन्ट्सहरू चाहिँ अलि कम नै देखिरहेको छ। तर अब किनकि हामीले यो रेकर्डिङ पनि भएको कारणले अलि अब युट्युब च्यानल पनि छ होइन हाम्रो डिपार्टमेन्टको त्योबाट पनि अलिकति अब अलि मासमा पनि हामीले सेयर गर्न सक्छौँ होइन।
मेरो एकजना साथी छ मेरो स्कुलको क्लासमेट ऊ चाहिँ नि युट्युब हेर्नु रहेछ। यो पुरा चाहिँ मेरो चाहिँ यो भन्नु लाइभ नहेर्ने अनि चाहिँ युट्युबमा हेरेर बस्नु रहेछ। मैले अस्ति यो हेरेँ त्यो हेरेँ ऊ म्याथमेटिसियन होइन तै पनि ऊ चाहिँ साथीको भनेर हेरेर बस्नु पनि केही नलेज त एड हुँदो रहेछ नि।
हो सर। अब यो टाइम नमिल्दाखेरि चाहिँ त्यसैलाई पनि हामीले गर्न सक्छौँ त्यसैको पनि हेल्प लिन सक्छौँ। सरको जुन पिडिएफहरू मैले रिसिभ गरिरहेको छु त्यो चाहिँ म एकैपटक त्यो कम्पाइल गरेर म पार्टिसिपेट हुनुभएको सर म्यामहरूलाई म सेयर गर्छु इमेल गर्छु पछाडि।
हुन्छ पिडिएफ
हुन्छ सर यति नै गरौँ होला आज।
हुन्छ हुन्छ ओके थ्याङ्क यू
हस्।
थ्याङ्क यू सी यू नेक्स्ट विक द क्यालकुलस